Now we can go through circular motion. The inquiry question in this is, why do objects move in circles? So, uniform circular motion is the motion of an object traveling in a circle at a constant speed. So in this case, the speed is constant. Velocity vectors are changing by therefore by the equation a equals v squared over r, acceleration is also changing. So that's something that's very important. And the fact that acceleration is changing, it might not even be touched on in this module, but it will definitely be touched on in things like module 6 and module 8 as well. So yeah, but these are kind of the constant features of uniform circular motion. The fact that the speed is always constant, the velocity vectors are changing because, well, the direction is changing, and so hence velocity is also changing, and the fact that acceleration is also changing due to the direction changing. So what does this mean then? F is equal to ma, acceleration is not equal to 0, force is not equal to 0, because again, distance is changing. So there's going to be a net force, and that net force is what we call centripetal force. So the net force is what net force inwards is what we're going to be calling centripetal force. That will be denoted by F is equal to mv squared over r, right? Because it's F is equal to ma. And so by the formula, or by the equation, A is equal to v squared over r, we can get F is equal to mv squared over r. So the definition then, centripetal force is the force that directs objects towards the center of a circular path. That's what you would say the definition would be. So, all right, so as I mentioned before then, centripetal force is a resultant force, and centripetal force always points towards the center of a circular path. So always towards the center. So because it will act in kind of the same direction as acceleration, always act towards the center of a circular path. And this will kind of come into play when we touch up on module 6, where you'll observe the motion of a charged particle in a magnetic field. But yeah, centripetal force always acts towards the center of a circular path, and centripetal force is also always a net force. So you don't end up drawing centripetal force in a force body diagram, because we don't end up drawing the net force. We only end up drawing like direct forces that act on it. So centripetal force is a type of net force or resultant force, and so we don't draw it in the force body diagrams. So doing this question now, find the centripetal force experienced by the mass with tension of 10 newtons and an angle at 30 degrees. Well, centripetal force is a resultant force and points to the center of a circular path. So what we do is we'd follow the steps, we'll draw the force body diagram, and then we'll resolve the vectors, right? Because it would be the net force. So if tension is acting like this, and I'm assuming the ball isn't just falling down, then that means that the vertical forces are balanced, which means that the only other vertical force that can counteract gravity can be the vertical component of tension. So the force so if I imagine a triangle like this, right? A triangle like that, this vertical component, hopefully you can see my cursor, if you can see my cursor, the vertical component of tension will be the force that counteracts the force of gravity. And so now the object won't be moving in the vertical direction. But there's a resultant force that points towards the center of the circular path, and this will be the unresolved horizontal component of tension. So in this case, the horizontal component of tension will act as the centripetal force. How would we solve the horizontal component of tension then? Well, we can do 10 cos 30, because cos 30, so 10 cos 60, sorry, because cos 60 will be this horizontal component, or 10 sine 30, same thing. So 10 cos 60 or 10 sine 30, depending on where you draw your triangle, essentially. If I draw my triangle like this, right? If I draw my triangle like this, if you can see my cursor, then the answer will be 10 sine 30 to find this component. If I draw my triangle like this though, again, hopefully you can see my cursor, the component would be 10 cos 60, and that will be equal to 5 newtons. All right, so what is then the centripetal force on a bank track? So again, it would be to draw diagrams. Force is the vector sum of the normal and weight force, right? Centripetal force will be the vector sum of the normal and weight force. And so to calculate, you should find the horizontal and vertical components of both forces and then add them. So I think this one will be a similar scenario to our tension question, where the normal force, the vertical component, will balance out with gravity, and then we have left the the horizontal component of normal force that will act as the centripetal force then. So yeah. Now we can move on to torque. So torque is the turning moment of a force. So we have torque is equal to Rf. The next tip is don't memorize whether to use sine theta or cos theta. So a lot of times you might see in textbooks or something, you might see Rf sine theta. So that is kind of misleading because it's assuming that the angle is directed in one way. What the actual formula is, and I'm pretty sure this is what's on your formula sheet as well, what it's actually looking for is Rf, so R perpendicular F. So when the force acts in the perpendicular direction, that is what they're looking for. So keep that in mind. So don't memorize whether to use sine theta or cos theta because it changes case by case. And a lot of questions are designed so you can't use the formula as itself. So you can't use Rf sine theta. You'll have to look at whichever way the force is perpendicular. So because I mentioned that now, we can say now, torque is achieved by applying a force perpendicular to the object.